Welcome to Financial Statistics. Imagine you want to buy a house in 6 months, but you are worried prices will skyrocket. What if you could pay a small fee today to lock in the price? That is exactly what financial options do. Today, we are going to explore the Black-Scholes formula, the mathematical recipe that tells us exactly what that fair upfront fee should be. It is one of the most important equations in modern finance. Before we dive into the math, let us understand what we are pricing. A European option is simply a financial contract that gives you a choice on one specific future date, known as the expiration date. A call option gives you the right to buy an asset at a locked-in strike price, while a put option gives you the right to sell it. The Black-Scholes formula assumes that the underlying stock price moves randomly over time, following a statistical pattern called a log normal distribution. By looking at time, current prices, and how wildly the price swings, it tells buyers and sellers exactly how much this contract is worth today. Now that we understand what an option is, let us look at the formula used to price a call option. Conceptually, this formula subtracts the expected cost of paying the strike price from the expected benefit of receiving the stock. The symbol C is the call option price we want to find, S is the current stock price, and K is the strike price. The term e to the power of negative r times t is a continuous discount factor, where r is the risk-free interest rate and t is the time to expiration in years. As the stock price increases, the call price increases because the right to buy becomes more valuable. This main formula relies on two intermediate variables, D1 and D2, which act as the engine inside the probability function. The symbol sigma represents the volatility of the stock, which measures how wildly the stock price swings. A higher sigma means bigger, more unpredictable swings, making the option more expensive. The natural logarithm measures the continuous return needed to reach the strike price. The variable D1 adjusts the probability by factoring in the expected value of the stock, while D2 represents the actual statistical probability that the option will end up profitable. N of x simply gives us the cumulative probability from the standard normal distribution. To truly grasp how this works, let us visualize the formula on a graph. On the horizontal axis, we have the current stock price, and on the vertical axis, the option value. The dashed line represents the intrinsic value at expiration. It is 0 if the stock is below the strike price K and rises steadily if it is above. The solid blue curve is the Black-Scholes price today, prior to expiration. Notice how the blue curve is always above the dashed line? That gap is the time value. Because there is still time left before expiration, there is always a chance the stock could shoot up, giving the option extra value, even if it is currently below the strike price. Before we move on, let us see this formula in action with a concrete example. Suppose a stock is trading at $50 and you want to buy a call option with a strike price of $50 expiring in half a year. The risk-free rate is 5% and volatility is 20%. We are asked to find the fair price of this call option today. Our strategy is to first calculate D1. We write down our formula and substitute all our known values. Notice that the stock price and strike price are equal, making their ratio exactly 1. This will make our calculation much simpler in the next step. Continuing with our calculation, the natural logarithm of 1 is 0, so the first part of the numerator disappears. We simplify the rest of the numerator to get 0.035. The denominator, which is volatility times the square root of time, evaluates to 0.1414. Dividing these gives us our precise value for D1, which is 0.2475. Next, we calculate D2 by simply subtracting that same denominator value from D1. This adjustment represents the drag that volatility puts on the probability of finishing in the money. We get 0.1061 for D2. Now, we have our intermediate variables. So we look up their cumulative probabilities in a standard normal distribution table. We plug these probabilities, along with our stock price, strike price, and discount factor, back into the main Black-Scholes equation. We calculate the two main parts separately. The expected benefit of receiving the stock is $29.885. The expected cost of paying the strike price is $26.445. Subtracting the cost from the benefit yields $3.44. This means you should pay exactly $3.44 today for the right to buy this stock in 6 months. Now that we have the price for a call option, what if we want to price a put option? We do not need to start from scratch. We can use a fundamental financial rule called put-call parity. This rule states that holding a portfolio with a call option and a certain amount of cash is mathematically identical to holding a put option and the underlying stock. Because these two portfolios have the exact same payoff in the future, they must cost the exact same amount today. If they did not, traders would buy the cheaper one and sell the expensive one for free riskless profit, which is called arbitrage. This brings us to the mathematical equation for put-call parity. On the left side, we have C, the call option price, plus the present value of the cash needed to pay the strike price. On the right side, we have P, the put option price, plus S, the current stock price. This simple equation is incredibly powerful because it links all these variables together. If we know the price of a call option, we can easily rearrange this formula to solve for the put option price by simply subtracting the stock price from both sides. Let us see how this saves us time. Let us apply this parity equation to a new example. Suppose you want to buy a put option on the exact same stock with the same strike price and expiration as before. We are asked to find the fair price of this put option. Instead of recalculating complex probabilities, we use our rearranged put-call parity equation. We already know the call price is $3.44, and we know the discount factor from our previous work. We substitute these known values along with the $50 stock and strike prices directly into the formula. This sets up a very straightforward calculation. Continuing with our substitution, we first evaluate the middle term. Multiplying the strike price by the discount factor gives us $48.765. This is the cash we need to invest today. We add our call price of $3.44 to get a combined portfolio value of $52.205. Finally, we subtract the current stock price of $50. This gives us approximately $2.21. The put option is cheaper than the call option because positive interest rates make the right to buy later slightly more valuable than the right to sell later. Now that we have used the parity equation to find a specific price, let us use it to derive a standalone formula for any put option. We are setting out to express the put price entirely in terms of the original 5 variables. We start with our rearranged parity equation and substitute the massive Black-Scholes formula directly in place of the call price, C. Next, we perform some algebraic rearrangement. We group the terms containing the discounted strike price together and the terms containing the stock price together. Factoring these out makes the expression much cleaner and sets us up for a final mathematical trick. To finish our derivation, we use a beautiful property of the standard normal distribution symmetry. The probability of being greater than a value is exactly 1 minus the probability of being less than it. Mathematically, 1 minus n of x is exactly equal to n of negative x. By applying this symmetry to our grouped terms, we arrive at the final Black-Scholes formula for a put option. This formula adjusts for the expected value of the stock we have to give up when we sell it. Notice that as the stock price decreases, the put price increases because selling at a fixed high price becomes incredibly valuable during a market crash. Before we conclude, it is important to understand the historical impact of what we just learned. When the Black-Scholes formula was published in 1973, it completely revolutionized the financial world. Before this, traders had to guess how much options were worth using rough estimates and gut feelings, making the market highly risky and inefficient. By providing a rigorous mathematical way to price risk, this formula allowed the creation of massive global derivatives markets. Today, every major bank and trading firm uses variations of this exact formula to price millions of contracts every single second. Let us summarize the key takeaways from our lecture. The Black-Scholes formula is a powerful mathematical tool used to find the objective, fair price of European call and put options. It relies on 5 key inputs: the stock price, strike price, time to expiration, interest rate, and volatility. By balancing the expected payoff against the cost of exercising the option, it removes guesswork from trading. Furthermore, put-call parity ensures that call and put prices remain perfectly linked. You have now covered the full topic, and understanding this formula is your ultimate key to mastering how financial markets price and trade risk.